Why not? Welcome back. Hello. Hello. Welcome back. Yes. So as I announced yesterday, I made some adjustments to the lecture and the example we're working on after the questions we had. So I wanted to start with that. The thing about the phi correlation and the p-values that I stumbled over. So first off, thank you for those of you who asked the questions about this because it forced me to be more specific. The problem with anything that each of us writes, right? We know what we meant. Whether it's a lecture slide, a paper, a set of instructions, or anything else, we know what we meant. So it's really hard to step back and assume the mental position of somebody who's outside yourself. So thank you for forcing me to do that and making changes to make things more clear. I'm very happy to be in the position to be able to do that. So what is this chi-square versus r thing? I wanted to remind you something we talked about a little bit a while ago. This little table right here. Test statistics that you are going to see. This is slide 26 of lecture 2. There are 4 that you will see used in quantitative methods. There's Z, there's T, there's chi-square, and there's F. Z and T are used when you're testing one thing, such as a correlation. The difference between them is whether or not they use denominator degrees of freedom in their distribution. Z does not, whereas T does. When you're testing more than one thing, meaning you have numerator degrees of freedom above 1, then it switches to chi-square instead of Z or F instead of T. You haven't met F yet. If there's only 1 degree of freedom, then Z squared is chi-square and T squared is F. So the reason that the p-values differ, got one more coming, here's one more. The reason that the p-values differ is because of these reference distributions. When you have a chi-square test for association between 2 categorical variables, it's using chi-square, which does not have degrees of freedom, whereas the corresponding Pearson correlation that goes with it is being tested on a distribution that does, with T. So the p-values are slightly different. Generally speaking, the p-values will be larger when you take into account denominator degrees of freedom, especially in smaller samples. So that was why they don't match. But the good news is that you already know how to get the correlation instead. You can run proc-core, and that will give you the correlation value and the p-value that goes with it using a t-distribution instead of chi-square. The other thing that I added was a picture of chi-square that I pulled up from Wikipedia. It's in here now. One second. That one. So that's what the distribution itself looks like. All right. So any questions on that? That's where we left off with last time.
Can you show me where the p-value is being reported on the readout?
It's not.
Okay.
This p-value corresponds to this chi-square. The p-value for this phi coefficient, which is a Pearson correlation, you would have to get from running proc-core instead, or pw-core in Stata. Okay? Or, yes.
I think what confused me last time is I have to run a separate test.
Mm-hmm.
And so I started plugging in the numbers from the Fisher's exact test, and the one it said was right was the two-sided PR equals B. So I just assumed that meant that was the P calculation. I didn't realize that. I
think you got lucky.
It would come from somewhere else. Okay.
Yeah.
So don't count on that.
Don't count on that, yes.
Typical way to find it. Go ahead
and run proc-core.
Okay.
And making the homework, that's what I did.
Okay.
So you should, if we go to proc-core and SAS, then the p-values show up in the correlation matrix. The comparable command in Stata is pw-core, where you ask for significance values that come with that. So yeah, because the answers are correct to 2 digits, it's possible that you entered a value that was sufficiently correct to trigger it as correct, but isn't the exact answer. Okay. keep the pretty picture up here. Other homework questions while we're on the topic. How's that going? It's going? Maybe? Have about a week to work on it, so no pressure yet. Let me know if you run into any problems. I'll keep asking in class.
I have a problem,
You have a problem?
but we might cover it.
But we might cover it?
Are we still going through the PowerPoint slide?
Yes.
Okay, so like because it's at the end of the homework.
Is it about power and type 1 error and that kind of stuff? One of those questions?
It's,
Let me pull up.
I think the last three questions, which of the following is true about the
Ah.
persons are between
Yep.
two things?
Yep. We haven't talked about that yet.
Okay.
We're gonna do that. Yep. All right. Let me see. And from the chat window, can you make one more statement to clarify about determining significance and rejecting retaining null hypothesis? Certainly can. Let me pull up a slide for that. Because we're going to talk about that also. The end of this lecture that we haven't gotten to yet. There we go. So if we decide to reject the null hypothesis, what does that mean?
This value is outside.
Of the subject.
It's
So It's
outside.
in one, yeah, it's in one of the tails.
Yes, our value is sufficiently unexpected, where we have defined a priori what time we're allowing unexpected, right? The traditional level is 5%, alpha of 5%. That's considered aberrant, unexpected, significant, reject the null hypothesis. If we decide to retain the null or do not reject, then we're saying the opposite. We're saying the result is not significant. It's well within expected territory. It would happen with decent frequency. It would happen within that other 95% of the time. We don't have enough evidence to say that the null appears to be, we don't have enough evidence to say that our data are different. The null is always the central point, whatever we expect. So that can be a population mean, say, of 12 ounces. It can be a correlation value of 0. It can be a lot of things. So, Melissa, did that help answer your question? See if the chat window pops up. Yes. Yes, great. Yes, with exclamation points. That's someone who's excited about quant methods, right? More than me, even. I've already had 2 cups of coffee today, so I have placebo do in place to keep me from going off the rails. But yes, we have some stuff to pick up in here. I skipped over stuff in the interest of time that I want to visit briefly. I tend to put more things in here than I necessarily want to go over just because I want you guys to have information for your future use. So a few of these things fall under that category. Let me pick up after Spearman. So you guys have learned so far 2 different kinds of correlations, right? Right? We have Pearson, which is designed to assess linear relationships between 2 quantitative variables. And we have Spearman, which is designed to assess the rank order variables instead. So that makes sense if they're ordinal or if you're concerned about extreme values. One of the things that people do incorrectly in practice is use either of those correlations to indicate reliability. There's another one that should be used for that instead. So let me draw you something real quick that will probably illustrate what I mean better than this. So let's say that I have one rater's rating scale here. This is rater A. I have another rater B. And I want to get an index of inter-rater reliability. So let's say the first person, rater A, puts here. Rater B thinks they're a little bit higher than that. They put them here. Second person, A, puts here. Same thing happens with rater B. Third person is up here. Rater B thinks they're up here. Are these 2 reliable? If I were to estimate a Pearson correlation between the rating provided by A, correlate it with the rating provided by B. Yeah. That correlation would be 1, or very near to it, within the constraints of my paint drawing. Now let me ask you a different question. What if you were trying to use these ratings to decide to further someone's treatment, put them in a special program, give them an additional opportunity of some kind, and you have a cut score on this measure, after which they're eligible to participate? Let's say the cut score was right here. Whose rating are you going to use? Absolute values matter in assessing reliability, not just if people put the rank orders the same, but the actual numbers themselves. So you want to have a statistic that understands that no, B looks like it's not reliable because rater B is systematically higher. We don't want to use Pearson's correlation because what Pearson's correlation does is standardize each variable and then look at the relationship. We want them to be unstandardized so that we can keep track of actual distances between the numbers. So to be able to do that, you need something called an intraclass correlation instead. This shows up in a lot of contexts, but it's a measure of reliability. The trick to this, the difference, is in both variables. If you're correlating 2 people, for instance, they use the same mean and the same variance. They share it. So rather than having 2 means and 2 variances to standardize, they do it against 1. That way you can keep track of actual distances between observations. The good news with this technique is that it's expandable to more than 2 raters. So let's say that you have a study in which you're doing some sort of coding, like you're watching videos and making tallies of behaviors or something like that, right? Not all of your research assistants are going to code all the videos. You might have 10 coders and each person does so many videos. Well, how do you measure reliability in that context? As an agreement between the coders. If you think about it as rater A correlated with rater B, that falls apart when you have 10 people and not everybody rates everything. But with this method, you can phrase it as proportions of variability that are due to raters, due to the subjects they're rating. That can include multiple raters and multiple subjects. And so if you're interested in this, I can point you towards other literature, but this just ask the Google for intraclass correlation if you're doing reliability assessments with correlations, okay? Okay, there. I'm not going to do a homework on that or anything. I just wanted you to be aware of it. Part of the difficulty in learning new things is knowing what terms to ask for. So there's a Google phrase for you. So here's just an example with a couple numbers where you would end up with a different index of reliability whenever the means and standard deviations differ across 2 raters. Now the thing that your question was about, blanking on your name, Jacob? Yeah, I was a second behind. It came to me then. Binary variables. So one of the problems with binary variables is that they don't have a lot of information, right? You only have 2 possible values. That's not a lot of information. It turns out that to the extent that binary variables mean differs from 50%, a possible correlation that variable can show with another binary variable is limited. So here's a chart that shows you the relationship between what the proportion is on each variable and what the maximum correlation could be. So for instance, if you have a variable x where 10% of the people have a 1 and 90% of the people have a 0, you want to correlate that variable with another variable y where 20% of the people have a 1 and 80% have a 0. If those things are perfectly correlated, the highest your Pearson correlation can be is 0.67. So while valid, more question, for binary variables, Pearson's correlation is not ideal because of this problem. What you do instead is something that will show up in advanced stat courses. Again, not something I'm going to ask you to do, but these are words that you may hear, and I want you to be aware of the fact that they are different. So if I have a correlation between 2 binary variables that's a Pearson's correlation, I could also call that a phi correlation. Those are the same. All of the words on this slide are not the same. Tetrachorics, biserials, polychorics, and polyserials. These are correlations that are designed to overcome that range restriction issue. They are more computationally intensive, They are the basis of latent variable measurement models that you might take, like I'm teaching a class on that this fall. So I just want you to have seen these and know they're not the same. This is something that you would want to learn about if you plan to work with binary or ordinal outcomes, because these show up in models that underlie those, but they're not Pearson's correlation. These are something different. Then we do crosstabs in chi-square. The thing about chi-square is that you're directly calculating a test statistic. Like the test statistic from this example that we did last time was a chi-square of 7.71. What is that? Well, I can tell you whether or not it's significant. So on this chart, for instance, this is the new slide that I added. For one numerator degree of freedom, which is what it is if you have a 2x2 table, the yellow line shows the expected chi-square distribution. So I can decide how unexpected our result is relative to this distribution and say it's significant, but it doesn't give me an effect size. It doesn't give me an index that I directly know what it means, the way that correlation is something that I directly know what the value means. But the good news is that we can fix it. So here are some other variants for cross tabulations and chi-square type tests that you might hear. I've highlighted two that are probably the most common: exact tests and kappa. If you're trying to establish reliability across categorical outcomes, so the rater has to make a qualitative distinction, kappa is used for that. So you may come across that in that context as well. But back to our problem. It turns out that we can convert any test statistic back into an effect size. There are two effect size measures, two families that you will see most frequently. One of them you already know, it's correlation. Correlation as a generic concept is an effect size. It ranges from -1 to 1, so we know immediately what it means given the value. Another one that you will come across is D, Cohen's D, in fact. That's a standardized mean difference. It tells you how far apart two groups' means are in standard deviation units. We'll get to that one next week or the week after. But we can compute R or D from any test statistic. So for instance, here's the formula to take chi-square into a Pearson's R. If I have a T, I can compute that back to R as well. So test statistics have two things embedded in them: sample size and effect size. We want to be able to separate out those things in reporting. So it's not just enough to know that something is significant. We want to be able to characterize the absolute magnitude of the relationship that we're describing. Another type of effect size that you will see for these sorts of cross tabulations, risk ratios and odds ratios. So for instance, if I have a different table here where I'm looking at whether or not people had a heart attack as a function of whether they received aspirin or a placebo drug, most of the people, fortunately, did not have a heart attack. So it's hard to look at these numbers without taking into account the sheer difference in magnitude of the occurrence of heart attack versus not. So a way to convey that more directly is what's known as risk or risk ratios. So 104 people out of the total who are on aspirin had a heart attack, whereas people on the placebo, 189 out of the total. So that's a risk of 0.94 or 1.71. If you divide the two, that's what's known as a risk ratio. So that's an effect size that you'll see commonly in public health, medicine, and those kinds of things, because they're interested in conveying the relative size of these things. Another one that you'll come across is an odds ratio, or a computer that restarts itself for no reason. That's weird. Maybe it's the projector's out of batteries or something, because I didn't touch anything. It's red and orange. Well, that's bad. Well, it's coming back to life. It's making noise, so that seems promising. Chat window says, it looks fine here. Yeah, the Zoomers are like, what's the problem? I can still see the screen.
Did the bulb burn out?
That's what my hypothesis is.
Can I go get help?
Sure, if you're willing.
Okay.
Oh, yeah, they shut off. That ain't good.
Yeah.
Yeah, we'll
The office is like. Yeah, I was gonna go to the desk.
Yeah, the people at the desk hopefully should be able to. Oh, you mean the children that watch HGTV and
Yeah, who
sports?
sit on
Yeah.
their computers. I would ask Evans or John.
Yeah, well, they look like children to me, I'm sorry.
They are.
They're, you know, yeah, so, yeah, okay, Zoomers, we're taking a quick moment to see if we can solve the projector problem because it just died in the middle of class, and if not, well, you've got the stuff in front of you, so we can keep going. Odds ratios, relative risk ratios, and then we get to the cool stuff, decision summary. So we'll see. Come on. Now my computer is like, what are you doing? I'm as long as I tell you what I'm looking at. And don't expect you to just to know that for no reason. Let's see. Since we are on hold, quick question. Do I remember that we have an in-class test? No. I've never given a test in my life. I'm not about to start now. Yay.
There's lunch.
They what?
He's on lunch.
He's on lunch. Okay, well, we may not have a projector anymore. We'll do this like it's 1995 again or something, right?
We should be coming.
Hey, our savior. It just died. I swear I didn't break it.
I didn't break it.
Is it angry?
Yes, you looked at it wrong, I think.
Oh, okay. I'll try not to do that.
Plug it and plug it back in again.
Yeah.
Yes. It gets to a
Correct.
terminal state and it just shuts itself off for no reason. And of course you unplug it
Okay.
and plug it back in.
Yeah, so-
I know it sounds horrible, I'm sorry.
Zoomers
IT
tech
crowd.
support is here and they just unplugged it and plugged it back in. Which solves the problem a lot of the time. I just can't reach it. So. Yes, no
You need
in-class
to be at least
tests.
5'10", sorry.
Yeah. And we're gonna shut that down and start it over again?
Yeah.
Okay. We'll see. Anybody have any good weekend plans? No?
No.
Not really. As long as my taxes done.
Get your taxes done, yeah.
I might go swimming.
Okay, that's good.
Am I the only one that-
Self-care? No, I agree. I'm excited to leave my house, maybe voluntarily during the weekend. That hardly ever happens. I might put, shoes on and everything. So,
It's going to get replaced with a TV soon enough.
okay, cool. In terms of the rest of the example 2 handout, that shows you how to get risk ratios and odds ratios. Those are the extra words that show up on the proc freq line. That's not something I'm going to ask you to do, but it's just sort of an FYI in case you want to do those things from cross-tabulation tables. So that's what the rest of that is. It's a little trickier in Stata than in SAS, but they have more options for different types of risk and odds ratios that you could examine. So it's really thinking hard about it.
I wish it would shut down faster, it's ridiculous. They want to make sure that everything will be. This button would turn it back on, but now they've got it so it's hot, not hot wired.
Ah.
So you actually have to shut it off, turn it back on.
Ooh, promising. Smart. Now, I beg to differ.
Actually, the smart words that use the Epson projectors were a lot easier because they seem to hold up better. These smart branded ones weren't as smart.
More to smart.
I think we're good.
Okay, let's see. We're go, 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 go. Thank you for your help.
Sorry, it happened on days.
Okay, good to know. 5. Come on. Yeah, we're back. All right, we got it. Okay, we're back. Here's where I wanted to be. Summary on 46. So this is what we've done so far. Measures of bivariate association. between quantitative variables, between ordinal variables, and between categorical variables. Any other combination is going to be optimally handled in a model. That's what we're starting next week. We're starting to model, getting really excited. This is where the cool stuff happens. Models are how you answer questions. They're way more flexible and powerful than just these sorts of measures of association because you can control for stuff. Are these two things still related after I factor in potential confounds? Those sorts of questions are answered by models, which is why they're very exciting. But in making any decision about the null hypothesis, we can screw up our decision in two distinct ways. So I want to make sure that we have time for this because this is important. So what we've done so far, any sort of hypothesis test, meaning we're comparing our result to some sort of expectation. The expectation is the null hypothesis. We need a test statistic and its distribution. Our friends t and z if we're testing one thing. It'll be f and chi-square if we're testing more than one thing. We need a rejection region. That's alpha. What are we calling aberrant? How much of the time are we saying is sufficiently unexpected? So for instance, if I say alpha is 0.05, that means 5% of the time this result would happen if the null hypothesis were true, and 95% of the time is in the expected area here. So in two-tailed test lands, we're willing to accept unexpected in either a positive direction or a negative direction. But the total area, the red part, would be 5%. 95% is in the middle here. So in making a conclusion about whether something is significant or non-significant, meaning significant goes with unexpected, non-significant goes with expected, significant goes with reject the null, non-significant goes with retain or do not reject the null. Here are the two ways we can screw this up. Type 1 errors and type 2 errors. Have you heard of these before? A little bit? Yeah, big nod. Okay. Alpha is the thing you already know. That's also known as type 1 error. It is the probability that you found your result by chance, basically. We're willing to accept 5% of the time, for instance, that we would say, in fact, there is a relationship when there's not one. It's unexpected, but that doesn't mean that it's guaranteed. So in social sciences, we tend to be more concerned about making this type of error. A type 1 error is a false alarm. We thought we had something, but we don't. The other kind of error is type 2 error, which is represented as beta instead of alpha, and that is a miss. That is, you had something, but you didn't find it. There really is an effect, you just missed. So if we decide to reject the null, if we decide to say I have significance, then I have to worry that I'm making a type 1 error. If I decide the other way, if I retain the null, I say non-significance, then I have to worry that I've missed something, and that's a type 2 error. Here's a picture that can help clarify the trade-offs here. So if you set an alpha at 5%, then you are willing to have more type 1 errors than if you set your alpha at 1%. You have a bigger realm of that you're declaring unexpected. 5% is unexpected versus 1%. So if you're worried about making an error, if you're worried about making a false positive, bump your alpha down. And then you have less of the distribution that would be considered unexpected. But then the trade-off is that you're more likely to make more type 2 errors. You're more likely to miss something. You make it harder to find something. So if we look at this picture here, the dashed line is HO. This is truth. What we have is the alternative over here. If I set an alpha of 0.05, that's this gray section right here. It makes it easier to say that we are in unexpected territory. If I set the alpha at 1%, it makes it harder to say that we're in unexpected territory. But if it's harder to say it's unexpected, we're more likely to miss things. The red section here conveys the type 2 errors. So there's a trade-off. What kind of error is more problematic? It depends entirely on your research context, right? What is the cost of missing something versus the cost of a false alarm? For whatever reason, type 2 error rate is usually set at 20%. The way that that is phrased in practice is power, which is your chance of finding something if it's there. So we want to have 80% power, which means 20% type 2 errors. So type 2 errors are not as important in practice if you look at just the percentages as type 1. All right. Let's see if I want to say anything else about that. Yeah. So this is trying to put it all together here in terms of the words. The things that you would want to report out of any kind of analysis. The statistic that you got. Numerator degrees of freedom, that's the number of things tested. Denominator degrees of freedom, that's based on your sample size. The p-value that comes from your test statistic, as well as an effect size. Effect size tells you how big of a relationship there is in an absolute sense. Whether or not that is significant depends on your sample size. If we reject HO and say that something is significant, we do have to worry about type 1 error. We don't have to worry about type 2 error. If we do not reject HO, if we retain it, and we say our result is non-significant, we don't have to worry about type 1 error. We do have to worry about type 2 error. We have to worry that we've missed something. And in planning studies, what you want to be able to predict is how many people you need to have an acceptable power rate. 80% power corresponds to a 20% type 2 error rate. 20% rate of misses. 80% rate of hits. So the stuff that I gave you, the 3 extra files, are helping to convey, first things first, this one is the effect size conversion. This is how you can get an R effect size or a D effect size no matter what you're doing. So you can convert it out of T, Z, F, or chi-square with these formulas, as well as across, you can go back and forth. So this is just for your reference. The other thing, these are power tables. So this is a very simplistic approach to sample size planning. But this allows you to anticipate how many people you would need to have a good enough chance of finding an effect. And it depends on the size of the effect and what good enough chance is to you. So let me take you to, for instance, R, which is the second page on here. This first table is for a 2-tailed alpha. Let me see if I can get this thing on here. So let's say that we're willing to power up for a correlation of 0.5. That's what I expect to find. I want to know how many people I need. Well, if I have 8 people, then I have 25% power of finding it. If I did the same study of 8 people over and over and over and over again, the correlation estimate would be significant only 25% of the time. If I keep going down the column, we get down to the magical level, 0.8 right here. If you want to have an 80% chance of detecting an R of 0.5 as significant, you need at least 28 people. Now in practice, this is not how power analysis works. The number of people that you get is the number of people that you get, right? It does no good to look at this table and say, okay, I need to recruit 319 people. if you can't possibly recruit 319 people. So what do you do instead? What's known as a sensitivity analysis. You take this and spin it backwards. You start with what is possible. Let's say that I know I can get 50 people. I have the resources and the sampling to be able to get 50 people. What can I do with that? Well, if I go to my 80% power line, 50 people is going to afford me sufficient power, there's 46 people, to detect an R of 0.4 or greater. That's what's known as a minimum detectable effect size. So whether or not something is significant, whether or not you're calling it unexpected, whether or not you're rejecting the null is a function of effect size and sample size. And I wanted to show you how this works in practice with this paper right here that I sent you. The background to this paper. When I was an undergraduate in psychology, I took a 400 level, like upper level social psychology class, and I had to do a project on it. We had to find something to review and present to the class, and at the time, the book Emotional Intelligence had just come out, EQ, have you heard of this? So I read the book, and inside the book, they cited a line of research with these folks here, and I went and got this paper and read it. So this, one of the things the book cited is that children who are able to delay gratification turn out to have better outcomes down the road. There's a classic test, I think of it as called the marshmallow test. Have you guys heard of this? Oprah did a special on this one time and it was impossibly cute to watch. But the premise is that you take a kid into a room and you say, all right, I'm gonna leave you here, don't eat the marshmallows. If you can not eat the marshmallows until I come back, you can get 2. So can they wait, right? And so there's all sorts of ways, they're trying to distract themselves or otherwise. The kids that could wait had better outcomes. That was what the book said. And so I went and got the paper that followed these children longitudinally, highlighted the sections that are relevant here. In particular, there were 4 kinds of strategies that they tested these kids with when they were preschoolers. They then followed these kids up until they were in high school and measured their SAT scores. And the kids who were able to delay gratification had higher SAT scores. That's what the book said. That's not actually what happened. And I remember being like, ah! So this is a good example of how power is important in making conclusions. So the people that they followed up differed across the 4 conditions that they had. Some of the conditions had more people that they were able to follow up for whatever reason. Here's the data. Here's the conclusion that they drew here. The observed differences between conditions are consistent with the expected. Preschool delay time, so the amount of time that they were able to delay eating the marshmallow, correlated positively with SAT scores when the rewards were exposed and no strategies were conditioned. Otherwise, it didn't correlate. That's not actually what happened. There's the table. I'll try to blow this up so everybody can see it. Okay. These are Pearson correlations between verbal and quantitative SAT scores within each of these groups of participants. One that they are excited about is the one with the stars. What stars mean? Significant. And this more stars means more significant. The p-value that corresponds to a correlation of 0.42 for a sample size of 35 is significantly unexpected at the level of p less than 0.05. 5% of the time, if there were no association at the sample size, then you would see a correlation that big. And it's less than 0.1% of the time for quantitative. That's the thing that was in the book. But let's look at the other column, shall we? In particular, this number right here. That's a negative correlation, meaning that the kids who are able to delay gratification in that condition ended up dumber instead. it's almost the exact same size. Isn't that interesting? It's the complete opposite result that they predicted and didn't bother to mention it in the write-up or in the book because there's no stars next to it. How can you have a correlation of 0.42 be significant, but a correlation of minus 0.4 not be significant? It's not the minus sign. Because a negative correlation and a positive correlation are the same in terms of the number here. It's just a different pattern of relationship. How can this be? Besides effect size, what else goes into significance? Sample size. There were only 14 people in this condition.
Ah.
This, you don't have enough power with 14 people to declare a correlation of 0.4 significant. Question from the audience here. Sample size, yes, exactly. So with 14 people, what could they have done? Let's go to my power tables. If I check my magical level of power of 0.8, that means I'm accepting 80% hit rate, 20% as a miss rate of finding something with 14 people. I need to have a correlation greater than about 0.65. 14 people falls right in between these two numbers. So it's not enough to declare significance or not. If you have a ton of people, even tiny little relationships can be significant. Like 0.1. If you have over 1,000 people or so, you can find a correlation of 0.1 and declare it to be significant, unexpected, different than 0. But is the correlation of 0.1 something to write home about? That's very small effect. In certain contexts, that might be something to write home about, but just declaring it significant is not enough information. Sample size, yep. So I think that their conclusion that this was the only condition where we saw a relationship, this 0.42, is somewhat suspect. They found a relationship of almost equal size in the opposite direction, but they didn't have the power to declare it significant. So in this 0.42, what is my type 1 error rate? The answer is right there in front of you.
Oh. 0.05.
Mm-hmm. Less than 0.05 is my type 1 error rate. That is the likelihood that this is a false alarm. We set that. That's what choosing an alpha level means. Mm-hmm. What is the type 1 error rate for a correlation of 0.57? Yeah, it's a lot less. It's a stronger effect. It's less likely to be due to a false alarm. What is the, let me go over here. This next column, this minus 0.12, that one has a much higher type 1 error rate. That's what it means to be non-significant. It didn't hit the threshold. Type 2 error rate is then relevant instead. So if I want to track down, let's use this one instead, minus 0.3. If I have a correlation of 0.3 on a sample size of 33, what are the chances that I'm making a type 2 error by declaring it non-significant? The answer is not here. The answer is over here. So here's my correlation of 0.3. On 33 people, I'm somewhere between these two cells right here of 20 and 42. If I have between 25 and 50% power, What's my type 2 error rate? How are the two related? Power is the probability of finding an effect that's really there. Type 2 error is the probability of missing an effect that's really there.
So that's 1 minus.
1 minus. So if I accept a power of 0.25, 75% type 2 error rate. The probability of missing something that's there would be 75%. That's bad, right? So we don't plan studies with 20 people if we can help it. If we can help it, right? People are hard to come by, though. But this is the thing you have to know going into it. What are the chances you're going to find something significant? It depends on the strength of the effect you're looking for and the number of people with which you're looking for it. What if I have a giant effect, R of 0.7? 20 people? More than enough. 20 people all the way down here if I have an R of 0.7. So that'd be a 5% type 2 error, 95% power. 5% of the time, I would have a non-significant result in the long run. So in terms of screwing things up, if you declare something to be significant, unexpected, it's potentially the case that the false alarm. That's type 1 error. The opposite problem, if you declare something non-significant, potential that you missed something that was there. That's a type 2 error. Power is the chances of hitting something that's there. Type 2 error is the chances of missing something that's there. Type 2 error is 1 minus power, or vice versa. When does this show up in practice? Reviewer 3.
I don't like that guy.
Yeah. It could be, it doesn't have to be a man. It could be anyone. Reviewer 3 doesn't sign their reviews usually, so we don't know. But when do they get to yell at you about power? When is that something that you would have to be worried about? Under what circumstance? When you have small samples, but more specifically, what kind of decision would you have made that they could criticize about power? A decision to say something is significant, or a decision to say it's not significant? Not significant. The way that you answer such criticisms is to figure out the effect size. If something is not significant, it could be for one of two reasons. The effect itself is small. There is no relationship, or the relationship is tiny. Or you don't have enough people to find it. So if I say that something is non-significant, I would want to have an effect size to go with it. It's not that it's non-significant because I didn't have enough people. It's non-significant because it's a small effect. For example, a correlation of 0.1 is a tiny effect. Because 0 means no association, and 1 is perfect association, and -1 is perfect in the opposite direction. Another way to think about correlation is if you square it, it's variance that's overlapping. Have you heard that before? Venn diagrammy things? Shared variance? No? Okay, then that won't help. We'll get there later. But yeah. So the point that I'm trying to make is that in all of these things, we have to keep in mind effect size and sample size leading to the significance decision. And in study planning too. All right. I think I hit most of the stuff that I wanted to talk about today. How are we feeling about all of this? Not too bad? So would you know what to do in a given situation yet to answer questions involving real data? Yes, we'll see. Yeah. Well, you'll get a chance to practice that with your homework. We'll get the chance to start modeling next time. We have a question from the audience. Let's see. Sorta. Okay, well, I'll take sorta. Cautiously optimistic would be like a good place to be right now, right? Like, I feel like maybe I can do it. So, how would you decide then which version of things you need to do? What if I wanted to look at the extent to which, let's go with preference for pet is related to age. Have we done that one yet? No. Could I use Pearson correlation to examine preference for pet as related to age?
What's our sample size?
What's our sample size? So let's say that 1 is dog, 2 is cat, 3 is bird, and 4 is, give me something else.
Rodent.
Fish. All right. Yeah. Oh, yeah. And 5 is hamsters and gerbils. I'll put them in the same category, right? How can I put that variable into a Pearson correlation and look at see whether it's correlated with age?
Rank order.
It's rank order. I'm saying you have to pick one as your favorite.
Which one?
Mm-hmm. That's the question. You have 5 choices, right? We just figured out cat, dog, bird, fish, and some kind of hamster thing. Can I do a Pearson correlation on a variable like that?
There's too many variables, isn't
I think you have to do a chi-square first.
Can I do a chi-square on age? Mm-hmm. If it were younger people, middle-aged people, and old people, I could. But what if it's continuous?
there? Can't do that.
Would a Pearson correlation between favorite type of pet and age make sense? What kind of association does a Pearson correlation reflect? Linear.
Linear.
So I have 5 numbers, right? I have 1, 2, 3, 4, 5, but are they numbers?
Not really numbers.
They're not really numbers. So can I have a linear relationship with something that's not a number?
No.
No.
So it would be Spearman.
Not even.
No.
Not unless you're willing to say that there is a ordinal order of favorite type of pet.
No.
Yeah, so that's one that you guys haven't done yet.
So what would it be?
What would it be? It would be a model.
Oh.
Oh, see, that's not fair.
That was tricky.
No, it is fair because that's a homework question. There's a homework question like that. So I'm sowing the seed there to think about the types of things that I asked you to do. Some of the statistical tests that I asked for made no sense. Did SAS and Stata happily do them for you anyway? Yeah, they do. So if we had 2 quantitative variables where the numbers are numbers, right, that's what Pearson's is for. If we had 2 categorical variables, like if I had age group, I could have a chi-square cross tabulation of age group with favorite type of pet, but not if age were continuous. We need a model for that. Do you think it would be a good idea to chop up age groups so that I can put it in a chi-square? Let's say that I have age as an actual continuous variable, like years of age, like I have birth dates. Should I cut it up into like young people and old people?
it depends on how large your data set is, and if you can look at that much data at one glance. If you wanna put it in-
I would argue that it rarely makes sense to cut it up.
Oh, okay.
You're destroying information if you do that. So you will be tempted at times to try to simplify variables because you're not sure what to do with them. Resist the urge. We're going to put them in a model. What we're going to be able to do to answer that type of question is we would predict age as an outcome, and we would put in variables that represent differences between favorite types of pet as predictors. So did you pick cat or dog? Cat or bird? Cat or fish? Cat or hamster thing? Hamster thing is gerbil, hamster, guinea pig.
Rodent.
I'm gonna
Bunny.
put, what are the little slimy, like, what are the ferrets? That's what I'm thinking of. They're like all, they like slink, kind of. Yeah, they're slinky. But yeah, because what that question actually is, if there is an association between age and favorite type of pet, that would show up as a mean difference. That people who like cats are older than people who like dogs, or people who like fish are older than people who like rodent thingies. We haven't done that one yet. So we can estimate Pearson's correlations on anything, but whether it makes sense is a function of what kind of variable it is. What about if I had a Likert scale response? To what extent do you agree with some position? Strongly agree, neutral, disagree, strongly disagree. What if I wanted to see whether agreement to that position was related to age?
It's two variables.
It's two variables.
It's
It is categorical, but it's a special kind of categorical.
It's like
Mm-hmm. So what's the difference between something like that versus favorite type of pet? Whether or not there's an inherent order.
order.
Yeah, whether there's an order, right? I could tell you what I think the best type of pet is, and you could tell me what you think it is, and we could both be right. But there is an inherent order in a Likert type question where it's strongly agree, and so forth. But it's still not numbers, right? So that's the other kind of correlation would work for that. Spearman. Ordinal stuff. Because it's just the rank order. It's just the ordering. So it would rank order age, it would rank order your choices, and it would look at a relationship between that. If you use a Pearson correlation or a Spearman correlation, what test statistic do you get? How do you know if that correlation is different than 0? How do you get your p-value? Where does it come from? What test statistic? You have 4 choices. T, Z, chi-square, or F.
Pearson's T.
T for correlation, yep. Pearson's chi-square, that's chi-square. So the thing about these measures is that in correlation, you get the effect size directly. Like that is the correlation. You have to go to extra work to get the test statistic to go with it. Get the T. From the T comes your p-value. Chi-square, it's the opposite. The chi-square is the measure of association. It is the test statistic, but you have to work harder to get an effect size for it. You can convert that into some kind of an R, if it's a 2x2 table directly, or a D, or risk ratios or odds ratios are the other types of effect sizes for those. But what kinds of questions you can answer with a bivariate association are very different than the kinds that you can answer otherwise. So have you heard that ice cream sales are correlated with murder rates? Heard that one? Does that make any sort of sense? What's the third variable in there?
Weather.
Weather, right. So would I be able to answer a question about To what extent are these things related to weather? Is that what's causing it with just a simple correlation? Mm-mm. Bivariate association. I'd have to have some way of putting them all together. That's what models are for. So that's where we're headed next, is this idea of being able to look at associations between variables while controlling for other variables. So ice cream sales predict murder rates. Cool. Do they still predict murder rates after controlling for how hot it is? Probably not. But a lot of research questions are phrased in that sort of language. Does this matter after controlling for X, Y, and Z other things? So that's where we're headed next. Are you excited? It is. This is the part where it actually starts to make sense and things that you would read in journal articles to be able to do this. So I'm excited to give it to you. All right. Any other questions before we adjourn a few minutes early? Okay, so new stuff on tap for next week. You should be able to answer every single homework question at this point. If you can't, let me know, and I'd be happy to help you. All right. Have a good weekend. Leave your houses at some point, right? Explore the beautiful spring weather.